So there was a question about the lab report. The lab report is due today for the Le Chateliers. Were there any questions on that? Did you figure out what was the reaction 12? Oh, Ag plus Cl minus goes to AgCl. Okay. And so we had this one, Ag plus Cl minus goes to AgCl. Solid. These type of equilibria where we're doing metathesis precipitation, this is a Kc, but it's given another name. It's called KSP. SP just stands for solubility product, but we're going to get to that much later. So there are different ways we could shift this. We could shift this right by adding more what? We could shift it right by adding more silver or more chloride. And that usually works. Like, for example, if I want it more precipitate, I'll just add more chloride. However, it doesn't always work, because there are side reactions that occur. So, for example, this one, if we take lead likes chloride also, and it forms a white precipitate of lead to chloride like this. However, if we try to do a Le Chatelier shift here, let's say we add more chloride, we have to watch out because of this potential side reaction. So what can happen here is Pb2 plus can react with 4 chlorides to form the tetrachloroplumate 2 ion. And what that means is here we have to be careful. We can't add too much chloride to try to shift this right, because what we're going to get is we're going to get a Lewis acid-base reaction instead of a metathesis reaction occurring here. And what this is going to do is, if we have precipitate like this, with 2 chlorides we'll form the precipitate. With 4 chlorides, we're not. In fact, the more chloride we add, the more lead we take out of there, and it shifts it back left. So we could have a precipitate here and then start dumping in a whole bunch of extra chloride and end up removing the lead ion and having a Le Chatelier shift to the left, which dissolves all our precipitate.
How do you account for that for trying to?
What we do is, when we do this, is we watch it carefully. What you're going to see is the cloudiness increase, and then plateau. And then what's going to happen is as you keep adding more chloride, it starts to decrease, and it becomes less and less cloudy, and eventually it just becomes clear. That's what happens. Okay, there was another reaction that was kind of weird, and it was this reaction, the copper 2 plus. Here, if you add a little bit of ammonia, do you know what happens? If you add a little bit of ammonia to copper 2, what happens is this. We end up with a light blue precipitate. This is a light blue PPT. Okay, how much ammonia is this? Well, this turns out to be 2 ammonias and 2 waters, 2 liquids. And what we end up with forming is copper 2 hydroxide plus 2 ammonium. Here. Now, this turns out to be what type of reaction? Well, it looks like a Lewis acid-base reaction, which it is, but it also can be classified as a Bronsted acid-base reaction, or a metathesis. Actually, it's not a Bronsted. Sorry, let me take that back. A metathesis reaction. And that's because of this. Ammonia is a weak base, And so this is a metathesis reaction here, even though it doesn't look like a metathesis reaction. And what do weak bases do in water? Weak bases, do they ionize, dissociate? No, bases don't ionize, they don't dissociate. Instead, they do what in water? Hydrolyze. And so we're going to have a base hydrolysis reaction, which is a Bronsted acid-base reaction here, which forms ammonium and hydroxide, or ammonium hydroxide. Ammonium hydroxide is a strong electrolyte, so it splits up into the ions here. It's not very stable. It much prefers to be ammonia and water. And so if I have this, it turns out that this is like less than 0.1%. This is like 99.9% ammonia and water. Actually, it's greater than 99.9%. And so it's heavily favored. And this is less than 0.1%. But we form a tiny bit of ions here. It's a weak base. Weak bases partially hydrolyze water. The Kb for this, or the Kc for this, there's a whole bunch of letters for these things. So the Kc for this is equal to 1.8 times 10 to the minus 5. 10 to the minus 5 is heavily reactant favored. But, it's not hugely reactant favored. But it's enough. And so what we have is we have 99.9% ammonia and water. So if you're going to buy ammonia, let's say I wanted to buy ammonium hydroxide. So you go to the chemical store to buy ammonium hydroxide, you know what? They're going to give you a bottle, and you take it back to the lab, and you say, wait, this is 99.9% ammonia. There's only 0.1% ammonium and hydroxide. Did you just get ripped off? And so you just go back to the store and say, hey, I bought ammonium hydroxide, but I only got 0.1% ammonium and hydroxide. I want a bottle of ammonium hydroxide. So they give you another bottle of ammonium hydroxide, you bring it back, and what's going to happen? It's the same thing. And the problem is this. When you go buy the chemical, it's not going to be labeled ammonium hydroxide because it's only less than 0.1% ammonium. It's going to be labeled ammonia, aqueous ammonia. And so when we buy this, it's aqueous ammonia. And therefore, in this equation, even though it's a metathesis reaction, we just need a tiny bit of ammonium ions and hydroxide ions to react. In fact, we'll need 2 ammoniums and 2 hydroxides. Just a tiny bit. And then the copper 2 likes hydroxide and it forms a precipitate here. This is what we call the complete equation. Then we have the ionic equation. Actually, this is not the complete equation. This is kind of the ionic equation here. This would be the net ion equation too. But we have this. Now, this is with a little bit of ammonia or dilute ammonia. If you have concentrated ammonia, do you know what happens? If we have concentrated ammonia, so if we add a little bit of ammonia, we get that. If we add a lot of ammonia plus concentrated ammonia, we don't get that. What happens is the concentrated ammonia reacts with the copper 2 to form this, which we call what? The tetramine copper 2 ion. This is the deep blue color. So when you probably did this, when you did this, you probably noticed a light blue precipitate that disappeared. Right? When you first add the ammonia, you get this light blue precipitate, but you keep adding the ammonia, and the ammonia will take out the copper 2 to form the dark blue aqueous copper 2 amine complex here. Do you recall seeing that? Yeah. So these types of things happen. They're competing reactions that can occur. You have Le Chatelier's going on, and so we try to figure it out. Here, this one does not form complexes. Well, actually, it does. It can form the dichloroargentate complex, but it's not so stable. And so here we can add excess chloride. We're okay. Here we can't add excess chloride. How do I know what forms complexes and what doesn't form complexes? How do I know? How do I know if something forms a complex or doesn't form a complex? Well, I just look it up in a book. You know, there's a table of complexes and you look. In fact, a good source for this is Appendix D. Appendix D, you look there and you can see a whole bunch of complexes, and then you can, just by observation, see what types of complexes form and what types of Lewis acid-base reactions we have. And so, for example, here you would see this being significant, but not here. If I add excess chloride, I'm just going to push the equilibrium to the right. Here, the same thing. To avoid a complex formation, instead we could use hydroxide. If we use hydroxide here, then we don't form a hydroxyl complex of copper 2. However, if we try to precipitate out aluminum ion with hydroxide, then we run into the exact same problem. With 3 hydroxides, no problem here. If I had 3 hydroxides, I'm just going to form a white, very gelatinous precipitate of aluminum hydroxide. But if I just add 1 extra hydroxide to this, you know what happens? So, for example, if I add 4 hydroxides, then I end up forming this. What would we name this one? Yeah, tetrahydroxyaluminate 3. And tetrahydroxyaluminate 3, what happens is I initially get a white precipitate, and then I keep adding hydroxide to get more precipitate, and the precipitate disappears because I'm shifting it back now this way because of the complex formation. So how do we know, again, how do we know what complexes form? We look it up in Appendix D and see, will it be a problem or not a problem? Here, it's not a problem. If I add excess hydroxide, I'm just going to precipitate out more copper 2 hydroxide. I'm not going to form a hydroxyl complex of copper 2. Now, we see all these observations, and obviously we want to understand these more deeply. We want to be able to predict. But, that's part of the scientific method. You do all these observations, and then you try to find patterns, and then you try to predict. But we're not going to go there. Yeah, we're just going to kind of leave it at the, at the observational pattern level. That's it. Okay, were there any other questions on the report for today? Okay, the next thing I wanted to talk about is the report for the other lab that we did. What was the other lab we did last week? Yeah, determining K by measurement. Officially that one would be due today, but there's no, I didn't tell you what to do for that particular report. Technically, I simplified that. When I told you the pH is the equilibrium hydronium concentration, I simplified that problem because that problem is a little bit more complicated than how I did it. And so I want to talk about pH a little bit now, which is the next chapter, chapter 16. So we're going to be leaving chapter 15. So since we're leaving chapter 15, I think probably the easiest way to learn chemistry is to do a lot of problems. You do a lot of problems and you get more familiar and more comfortable with material. So what I'm thinking of doing is starting probably today, we'll do like maybe a Zoom remote session, and I'll start looking at the problems in the chapter. I'll just work through the homework problems probably, or maybe some additional problems there. So we'll start that today, and I was thinking of starting it this evening. So maybe let's see, today's Thursday, maybe 8 o'clock or something? 9 o'clock? I mean, can people make it or not?
Sorry, I have a night class.
Until what time?
6 to 9.
6 to 9?
Record.
I'll record it so people can watch it. You work till how late?
I work from 7:50 to 2:50 in the morning.
Oh, all right, that's not going to work.
Work all night.
All right, I can't make it earlier. All right, I'll record it so you can just watch it.
Okay.
Then we'll do it like were you interested in attending this then? Maybe like what time? 10? Can you do 10 or is that too late? Or if it's going to be recorded, so and it's going to be just maybe 10 to 11 or something. We'll just look at the first block of homework, and then tomorrow we'll do it again, and the next day do it again, and just progressively go through. And I'll post these on Canvas. But I wanted to talk about what I did on the problem. I simplified it a bit because when we're doing pH. pH is the power of the hydrogen ion concentration. Or H3O plus. So what we have to do whenever we're doing pH is we have to look at something called KW. KW. So if I have pure water at 25 degrees C, I have a distribution of energies. Like this. And so if this is at 25 degrees C, and we're just looking at pure water, there's a tiny, tiny fraction of water molecules that have quite high energy over here. In fact, high enough energy that we can see something like this occur. An H2O liquid smashes into another H2O liquid, and they have to have the correct orientation, so we get this big collision here. And in the process of this big collision, we have a acid-base reaction occur here. Now, if I compare the energies, let's say hydronium versus water, which one's a stronger acid? Hydronium, strong acid. Hydroxide versus water, hydroxide. So this is extremely steep uphill energy climb. And so I said last time, if I had 1 billion water molecules, about how many can make this steep uphill climb? It's some negligible amount. So if I had 1 billion here, it turns out we're not going to call it negligible now. We're going to worry about it. And we worry about it, it's going to be about 4 out of 1 billion. So 4 out of 1 billion can make this steep climb. And if that's the case, you know what the molarity comes out to be? And so this is the way we do it. We do everything using an ice table here. And so water is a pure liquid. And so pure liquids, in equilibrium calculations, the concentration doesn't change. Its activity is 1. So we kind of ignore. And so what we'll do is we'll just say that we'll imagine that no water has collided yet. And so we'll start off with 0 molar and 0 molar. And so we imagine that, okay, we have water, and then we turn up the temperature up to 25. When we turn up the temperature to 25, then the waters can collide. And the waters collide, then we're going to get plus X molar and plus X molar. And then we measure the pH. You know when you measure the pH of pure water at 25 degrees C, what the pH comes out to? Yeah. And so it comes out to pH 7. That's actually pH 7.00, which gives me how many sig figs? It's not 3. In power functions, anything before the decimal is insignificant. This actually gives me 2 sig figs. Yeah, so whenever you have a power function, it's only the stuff after the decimal that's significant. So that's 2 sig figs. A pH 7 means that the hydrogen or hydronium ion concentration is equal to 10 to the minus 7.00 molar. And so that's the power of the hydrogen ion concentration. And then we get this into our normal scientific notation. It comes out to 1.0 times 10 to the minus 7 molar. So when I measure the pH of pure water, it comes out to pH 7, which means the hydronium ion concentration has the power of 7. It's actually negative 7. Now we change the sign. Okay, if the hydronium ion concentration is 10 to the negative 7 molar, what is the hydroxide ion concentration? Yeah, it's got to be the same because, for every hydronium, we make one hydroxide according to stoichiometry. So this has got to be 1.0 times 10 to the minus 7 molar, which means the power of the hydroxide ion concentration, what is the power, the exponent of the hydroxide ion concentration? So if we see this, the power of this is 7. And how many sig figs do we have? Well, the coefficient here tells you how many sig figs. There are 2 sig figs. So it's 7.00. So this is equal to the power of the hydroxide, which we call the POH. And so the pH and the POH of water is 7.00.
I have a question about the sig figs. If we're saying, maybe I don't understand the use of the word power function.
Mm-hmm.
So why would the 7 there be only 2, but then
yeah.
we're looking at 1?
Well, the 7 represents the exponent here. And when we're counting sig figs, would you ever count the 7 as a sig fig? No. And so this 7 is actually that 7 there.
Oh, so you mean one that's used as an exponent?
Right. And then the coefficient here is actually, if it's 7, if it's right on 7, it's 1, If it's like above 7 or below 7, then it changes the coefficient here. It's the properties of logs because the pH is, if you want to calculate it, the pH is the negative log of the H plus concentration, and the hydronium is 10, the anti-log, to the minus pH, the anti-log of the negative of the pH. This is log base 10. Okay, now an interesting thing happens. The interesting thing happens is what happens if we increase the temperature? What happens to the kinetic energy distribution if we increase the temperature? It shifts to the right. That means we're going to get more, right? If we get more reaction here, because there's more higher energy water molecules, then what's that going to do to the hydronium ion concentration? Increases it. If it increases the hydronium ion concentration because of the negative and the positive relationship here, it actually decreases the pH. Because if we increase, let's say we go 10 to the minus 6. 10 to the minus 6 is greater. That gives us a pH 6. 10 to the minus 5 is greater. It gives us a pH 5. And so what happens is the pH changes with temperature. In other words, if I increase the temperature, the pH goes down a little bit, not much. If I decrease the temperature, this whole curve shifts to the left and the pH goes up. Well, that's a hassle because, the temperature changes every day. The temperature is not the same. And the temperature in the lab today is not 25. The temperature in the lab today is like 21.2 degrees C. So at 21.2 degrees C, that's a little bit lower, which means our pH is a little bit different, right? Well, this is a headache. This is a headache because we want pure water to be pH 7. And so modern pH meters have an automatic temperature calibration. So they have a built-in temperature probe, and what they do is this. If the temperature changes, they'll always keep the pH 7 for neutral water. That way we don't have to do an additional calculation. And so it makes our life a little bit easier, but in reality, the temperature does change. In the old pH meters, there was a little knob, and the little knob was a little dial, temperature dial. So what you had to do is, if you want pure water to stay at pH 7, regardless of the temperature, you had to change this, which just offset the scale. So in modern instrumentation, water always has a pH of 7, pure water. In reality, no, water doesn't always have a pH of 7 because temperature will change it. All right. So what this means is this. If I add acid to water, then there are actually two sources of hydronium. The two sources are 1, the acid, and 2, the water. In the calculation that I did last week, I only accounted for one source. I only accounted for the acid. The reason I could do that is because I took a little shortcut. The reason I did that was I just assumed that the amount from water was going to be tiny. This is a tiny amount. And so if I assume the amount from water is going to be tiny, then no big deal. It's negligible, like the simplifying assumption. It's negligible. However, that's not always the case. So let's look at the pH scale. The pH scale, in the middle of the scale, 7. This is what we call neutral. So if it's pH 7 and we have a temperature calibration or adjustment on, it's neutral. And so pH is about 7 to, let's say, 9, 10, 14, on up. When we get to pH 14, this becomes strongly basic. When we get to pH 0 and lower, like negative, this becomes strongly acidic. Now, if I have a base, where's the hydrogen ion coming from? Let's say I have a strong base solution, like sodium hydroxide. Where am I getting the hydrogen ion from? pH is the power of the acid. And so if I have a strongly basic solution, like let's say 1.0 molar sodium hydroxide has a pH of 14.00. It's 2 sig figs here, 2 sig figs here. Where is the acid coming from? This is the power of the hydrogen ion concentration, which means the acid is equal to 1.0 times 10 to the minus 14 molar. This is strong base. Where is this acid coming from? This comes from what we call Kw. And this is Kw here. Kw is the concentration of the hydronium at equilibrium times the concentration of hydroxide at equilibrium. And so the concentration of hydronium is 1.0 times 10 to the minus 7 molar. The concentration of hydroxide is 1.0 times 10 to the minus 7 molar. We get rid of the units, and we end up with 1.0 times 10 to the minus 14. Now this Kw, people memorize this. This Kw is only valid at 25 degrees C. At higher temperatures, Kw is bigger. At lower temperatures, Kw is smaller. And so what this tells us is this. If I add hydroxide to water, the hydroxide ion concentration increases. So if the hydroxide ion concentration increases, which way does the equilibrium shift for water? It shifts to the left, which means the hydronium ion concentration is going to decrease. And so there's going to be a seesaw or a relationship between hydronium and hydroxide. Increase hydronium, decrease hydroxide, increase hydroxide, decrease hydronium, that kind of thing. And so what that relationship boils down to is this. If the hydrogen ion concentration is 1.0 times 10 to the minus 14, that means the hydroxide ion concentration must be equal to 1.0 times 10 to the 0 molar. In other words, 1.0 molar. And so this is what's happening here. The hydroxide ion concentration increases, the hydrogen ion concentration decreases. And this is minuscule, 10 to the minus 14, which gives us the power of 14. And so that's one way. The other way we could do this is by the power of logs. And the relationship between the pH and the pOH is going to equal the pKw. And so the pH plus pOH, well, what is the power of Kw? The power of Kw is 14.00. So the pH and the pOH have to add up to 14. So that's the case here. The pH is 14. What's the pOH? The pOH would be here. What's the power of the hydroxide ion concentration? Well, we look at the exponent here. The exponent is 0. And so the power of the hydroxide concentrations is 0. And so 0 plus 14 gives us 14. So we're going to have this relationship. If I add acid here, then the hydroxide ion concentration will go down. And so what we're going to have is we're going to have a multiple equilibria that occur here. And let's take a look at an example here. What was the acid that we, actually we didn't look at an acid. What was the base we looked at? Acetate? Acetate? Okay. And we looked at what, 0.1 molar was it? 0.1 molar. Okay. So we did this calculation, except we used, we took the acetate and water. Now bases hydrolyze water to form, in this case, acetic acid and hydroxide. The hydroxide that I form in this step is going to perturb Kw, because the more hydroxide I produce, the less hydronium I'm going to have in Kw. And so here, this is what we have. What was the K from experimental? What was the experimental K value that we got? The Thursday lab, 1 week ago. Did somebody write it down? No, doesn't quite sound right. Yeah, that sounds about right. Let's take a look. I have the data still here. Let's take a look. What it was. I'm going to do it forward here. Technically, when we solve for the K, I should have added or factored in Kw, which I didn't. But, oh, this is ammonium, sorry. We did ammonium, not acetate. So it looks like the experimental K that we came up with was 5.36, using all the data. Right, and that was the average of all the groups. So we'll go ahead and write that here. Times, that was the, oops, that was the pH, right. So we'll calculate the K value. Okay, let me show you. We should have done. So this is going to look kind of complicated because this would be more of a challenging problem. But what we want to do is we want to do this. What was the concentration of ammonium? It was 0.1 molar, just 1 sig fig, right? And then H2O, we blacked out 0 and 0. Do you remember setting this up?
Yes.
Do you have this calculation in your notes?
Yes.
All right. Everybody? Yeah, this is going to be kind of the report for this lab. And so we did the minus x here, right? And then we did the plus x here and the plus x here. And then at equilibrium, we had the 0.1 minus x molar. And then we had the x molar here and the x molar here. And then what we did was we said, well, we know the equilibrium hydronium. The equilibrium hydronium was determined from the pH. And so we said, okay, the equilibrium hydronium is going to look like this. That is, the equilibrium hydronium concentration is equal to 10 to the minus pH molar. And then we said, okay, that's going to equal 10 to the minus 5.36 molar. And then we punch that in our calculator. We take the anti-log of 5.36 and we came up with what? You ever written down? 4.36 times 10 to the negative 6 molar. Okay. The situation is this. When we measure the pH, we're measuring the total hydronium concentration inside there. There are two sources of hydronium. One is the ammonium that gives us hydronium, and the other is water. Water is going to give us some hydronium as well. And what I did here in this particular problem was I ignored the contribution from water. I ignored the contribution from water because it was going to be small. But how small do you think the contribution from water was going to be? And you might say, well, the contribution from water is going to be around 10 to the minus 7. But if it's 10 to the minus 7, then 10 to the minus 7 is significant compared to 10 to the minus 6, right?
Yeah.
But in reality, the contribution from water is more like 10 to the minus 8, 10 to the minus 9 molar. And the reason is because of this Le Chatelier shift. And so let me mention that here. So in reality, this is due to the total contribution. Now, we worry about who's going to be the biggest contributor to hydronium, the ammonium or the water? The ammonium. And so what we do is we start off with the biggest contributor, and we call it step 1. Ammonium is going to be the biggest contributor. In step 2, we look at how much additional hydronium are we going to get from water. We know that we can't stop water molecules from colliding. Water molecules are going to collide as long as the temperature is set at 25 degrees or above absolute zero. Or actually, it doesn't have to be above absolute. This is above freezing and hydroxide. So in reality, what we're going to have is this. Now, here, we start off initial. Water is pure liquid. We don't worry about it. However, it's this. We have to worry about Le Chatelier's principle here. And this is what we call the common ion effect. The common ion effect is this. The step 1 and step 2 have this as a common ion. And so from step 1, what we're going to do is we're going to drop this common ion here. So we actually don't start step 2 with 0 molar hydronium, like imagining it's just we're going to allow it to collide. What we're going to do is we're going to start this with X molar hydronium from step 1. Okay, then we're going to assume that nothing has collided yet. And so what we're going to do is we're going to have 0 molar hydroxide, because we're going to say, okay, now the waters can collide. But because of Le Chatelier's principle, the more hydronium we have here, the more it shifts it to the left and the less reaction we get. So rather than getting 10 to the minus 7 molar, we're going to get much smaller than 10 to the minus 7 molar because of this Le Chatelier's inhibition of the forward reaction. And so now the change is going to be this. The change is going to be plus Y molar plus Y molar. But Y, again, is not equal to 1.0 times 10 to the minus 7 molar. And so a lot of people write that because they think it's going to be the same as in pure water. It's not the same as in pure water. In fact, it's going to be much, much less than 1.0 times 10 to the minus 7 molar because of the Le Chatelier's effect. And the Le Chatelier's effect in this case is called the common ion effect. Common ion. We already have product. If we already have product there, then we don't need to make as much to get the same K. It's just math. And so we call it, because of the common ion effect, it's going to be a lot less than it would be in pure water. In pure water, there's nothing there to inhibit it. We don't have this X already sitting here, and the X is kind of significant. And so at equilibrium, we're going to have X plus Y molar hydronium, and then Y molar hydroxide. And then what I did was I did the simplifying assumption. You know, the simplifying assumption was this. I said that I'm going to assume that Y is going to be negligible compared to X. If I assume that Y is negligible compared to X, then I can just ignore step 2 and then just plug in over here. And, you know, that seems to be a reasonable assumption because my molarity is 10 to the minus 6 molar. And from this step 2, I'm going to expect a lot less than 10 to the minus 7, more like 10 to the minus 8, 10 to the minus 9, 10 to the minus 10 molar. Does that make sense? And so that's why I skipped this step 2. But we can't always skip step 2 here. This is step 2 for a, or we could factor it in. You know, if I factor it in, then the math just becomes a little bit more complicated. You know, when we have 2 unknowns, what do we need? 2 equations. And the 2 equations we're going to have are K from this, which is going to be the ammonia times the hydronium divided by the ammonium. So we can plug these in up here. And we know what this equals to. And then over here we have Kw. Kw is equal to the hydronium times the hydroxide. But when I have 2 equations and 2 unknowns, it takes time to solve that. And if I can make an assumption and the assumption is reasonable, then it's okay. But how can you justify this? I justified it in my head. I said, well, and the way I justified it is because I knew the magnitude of additional hydronium is going to be very small, but how do you know? How do you know? And so you're not allowed to take these shortcuts unless you can justify them, right? But I went ahead and did that. And so let's do a calculation where we don't take the shortcut. And the calculation where we don't take the shortcut, I can solve this, but I don't want to right now. We're going to solve something similar to this later. But let's go ahead and predict. So the second part of the lab was to predict the pH, right? Yeah, okay. The second part of the lab was to do what? We predicted the pH of a 1 to 2 dilution. Remember that? A 1 to 2 dilution. So let's go ahead and do that. And in this case, I'm going to factor in Kw. Because, I mean, it's even more dilute. So let's see if we get anything significant happening here. And so, again, it's going to be ammonium plus water. This is going to go to ammonia plus hydronium. Okay, the initial was 0.05 molar. Water is liquid. We're going to assume nothing's happened yet. You know, so we just mixed it, nothing's happened yet. The K value that we calculated was what, 5? Can somebody tell me what the K value was? Okay, that's the accepted K value. What was the experimental K value? 1.9? Okay, well, it was kind of off. In the afternoon, it was a little bit closer. 1.9 times 10 to the minus 10. Okay, we're going to use that. Did anybody calculate their pH based on this? No? Okay, now, you did? Oh, good. 5.28. Okay, now look at, I'm going to do an extra step here. Minus X molar, plus X molar, plus X molar. And so at equilibrium, we get 0.05 minus X molar, and X molar. And you got hydronium equal to, what was it? 5.28 was the pH? Okay, so the pH 5.28, which means the hydronium concentration was 10 to the minus 5.28 molar, which was what? Oh.
2.63 times 10 to the negative 6.
2.63 times 10 to the negative 6 molar. Okay, that's a hydronium ion concentration here. And that means the ammonia concentration must be what? The same, 2.63 times 10 to the minus 6 molar. And then how much of this did we lose? So this is going to be 0.05 minus I need 5 zeros. 1, 2, 3, 4, 5, and then 263. So let's carry some extra zeros here. And this is going to be 0.0499937 molar. Okay, then typically what we do is we double check. The way we double check this is to plug these concentrations back into K and see if we get 1.9 times 10 to the minus 10. But I assume it's probably correct. Okay, so this is where we left it. But the situation is the pH is the total hydronium concentration. And so we're going to get hydronium from ammonium, but we're also going to get hydronium from what? Water. And so we call this step 1. This should be the biggest contributor because ammonium is a better acid than water. Okay, is it okay to erase this? Yes. Okay. So the difference in this case is, okay, what's the common ion between step 1 and step 2? The common ion is hydronium. So what we're going to do is we're going to bring the common ion here and then place it here. And so we're going to get 2.63 times 10 to the minus 6 molar. And then we're going to assume that no water molecules have collided yet. So we'll start off with 0 molar hydroxide. And then what we're going to do is we're going to add. And so we get some additional hydronium and additional hydroxide from the collisions. But because of Le Chatelier's principle, having this hydronium here present already is going to push it to the left. And so we aren't going to get as much. In fact, how much are we going to get? We're going to get 2.63 times 10 to the minus 6. 2.63 times 10 to the minus 6 from step 1 plus x from step 2. Molar. And over here, we're just going to get x molar. X molar is just going to come from step 2, none from step 1. Here. Okay, now let's go ahead and solve this. We know that Kw is 1.0 times 10 to the minus 14. And we're going to do this. That's going to equal 2.63 times 10 to the minus 6 plus x times x. So this is a quadratic. When I have a quadratic, I can just use the quadratic equation solver, or I can try the simplifying assumption. Simplifying assumption is so quick, we'll just go ahead and try it. I'm going to try out the simplifying assumption. It's going to be 2.63 times 10 to the minus 6 plus x is just going to be 2.63 times 10 to the minus 6. And then I have x here. Okay, this is equal to 1.0 times 10 to the negative 14 up here. So let's solve for x. So x is going to be 1.0 times 10 to the negative 14. Divided by 2.63 times 10 to the negative 6. And I get an x equal to 3.80 times 10 to the negative 9. Okay, so we need to justify the simplifying assumption. So the percent change is going to be 3.8 times 10 to the negative 9 over the original. The original was 2.63 times 10 to the negative 6 times 100%. So I'm going to take this divided by 2.63 times 10 to the negative 6 times 100. And so the percent change is 0.14%. Okay, is that an acceptable percent change? Yeah. With a percent change this small, even if we did the quadratic, it'd come out virtually the same to the number of sig figs we're allowed. We're not allowed that many sig figs here. All right, so it looks okay. The simplifying assumption is okay. Now let's calculate the hydronium. The hydronium is going to be 2. Actually, let's go ahead and write this in decimal form. This is going to be 0.50, 1, 2, 3, 4, 5, 2, 6, 3. And then we're going to need 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And then a 3, 8. And so altogether, I'm going to get 0.5 zeros. And then a 2, 6, 3, 3, 8. Okay, did that change the pH much? Okay, let's go ahead and calculate the pH. If I stopped at step 1, the pH came out to 5.28. Is that correct? If I add the additional hydronium here, how much did the pH change? And so I'm going to go ahead and take the negative log of this. And so I'm going to go 0.5 zeros, 1, 2, 3, 4, 5, 2, 6, 3, 3, 8. And then take the log of that. And then the negative. Actually, oh, something happened with this. The pH based on this was 5.579. If I did 2, I'm only allowed 1 sig fig. Carrying extra. The pH, if I stopped here at step 1, what would that have been? So let me try that again. 2.63 times 10 to the negative 6. Take the log of that. 5.580. I'm only allowed 1 sig fig in this particular problem, and so this is going to come out to 5.6. What's the pH over here going to come out to? Did it really make a difference? Now, even if I went 2 sig figs, did it make any difference? No, it didn't make any difference. So this is the reason I skipped it. I skipped it because I predicted that the additional hydronium from Kw was only going to be like 10 to the minus 9 because I already had some hydronium in there to begin with. Does that make sense?
So for most of these reactions, would we operate under the assumption that it is going to be negligible? Or should we?
For most, yes. For most of the calculations, Kw is negligible. However, not all the calculations. Let's take a very simple example of where Kw is not negligible. This example is going to be 1 times 10 to the minus 8 molar HCl. What is the pH of 1 times 10 to the minus 8 molar HCl? So we know that HCl is a strong acid, so I'm going to get 1 times 10 to the minus 8 molar H plus and 1 times 10 to the minus 8 molar Cl minus. Cl minus is not a Bronsted acid or base. You know, it actually is a Bronsted base, but it's too weak. And so it's neutral. And so we have 10 to the minus 8 molar HCl. What's the power of the HCl concentration or the H plus concentration? 8. And so this is easy. The pH is equal to 8. And how many sig figs do I have? 1. So the pH is equal to 8.0. It's easy, right? But there's a major problem. Do you see the major problem? What's the major problem?
It's very small numbers, so times 10 to the negative 7 actually.
Yeah, that's one, but there's another major problem here. Do you see the major problem? You probably don't see it because you probably aren't that familiar with the pH scale. pH scale in the center we call 7 is neutral. Anything above 7 we call basic. Anything below 7 we call acidic. So what would you call 10 to the minus 8 molar HCl? You call it weakly basic, but is HCl a base? HCl is an acid. Is HCl a strong acid?
Yes.
Why would a strong acid give you a basic solution? It can't. It can't. This is wrong. This is wrong because in this case, this is 10 to the minus 8 molar. It's a very small amount of hydronium. That means Kw should be a more significant contributor. If we start off with 10 to the minus 8 and Kw contributes, let's say 10 to the minus 9, is that significant? Yeah, so if we start off with 1 and Kw contributes 0.1, that's significant. But do you know, in this particular case, we start off with 10 to the minus 8 here, we get more hydronium from Kw. In fact, Kw is going to be bigger contributor to hydronium than the acid itself. And so we get like 70% of the acid from water and only like 30% of the acid from the acid itself because there's too little of it. Although this is a strong acid, this is minuscule. Would you drink this? You could drink it. It would be no problem. You know, when I was taking high school chemistry, my high school chemistry teacher always said, you know, you take some HCl and mix it with sodium hydroxide and you can drink it. It's just salt water, right? So all year long or whatever, I was waiting for him to drink it. He never drank it. But, you know, I drink this without any sodium hydroxide at all. And in fact, you probably drink more than that out of the tap. Do you know what the pH of tap water is? Well, if you might not drink tap water.
It was like 4.
Yeah, it's like 4.5, right? 4 or 5, yeah, that's about it. So you drink more than this. If you drink it out of the tap. You might drink the basic water though. And so here, we cannot ignore step 2. But I don't want to do this problem yet. We'll do this problem next time. And so today, for the lab, you can, you don't have to do any kind of report. I just want to see your calculation. So you can just make a photocopy of your calculation and turn that in. Or if you don't want to do that, we don't need to waste paper. I'll make an upload link. So you can just take a picture of it, PDF, and then upload it. And I want to see your calculations. Last Thursday's lab, there were 2 calculations. Some of you did 3 because you did it with the other one. What? I need a record, otherwise I forget, and I forget to credit your score on the grade sheet. So if you just submit it and just scan, you guys have Genius Scan or Cam Scanner? Yeah, if you just do that, that would be great. I'll post the link up later. Okay, so today we're going to look at our crystals, and hopefully you got some crystals. If you didn't get crystals, let me know, because don't worry about it. If you didn't get crystals, we can always get crystals out of this, and one thing we could do to get crystals out of this is we can just heat it up to boil off some of the water. Maybe there's just too much water. Boil it off, and then pretty soon you'll get crystals. But you don't want to boil too much of the water off, because if you boil too much of the water off, you're going to start getting oxalic acid crystals and potassium oxalate crystals, the white crystals that you don't want. You don't want those crystals. You want those crystals to stay in the liquid. You just want your crystals to come out. Okay, now what we're going to do is we're going to do the vacuum filtration with the Buchner funnel. So you're going to check out the Buchner funnel from the stock room. And we'll set up the apparatus, and it's very shaky, so usually we'll clamp it onto one, and so we'll put the trap, on one side and the flask on the other side, and then use a utility clamp. The utility clamps are underneath the bench over in the corner over there.
How far are we going this time?
We're going pretty much to the end, except we're not going to weigh it. We're going to dry the crystals over the weekend. And that way, yeah. So we'll weigh it next week. But you guys are going to do you guys remember the recrystallization? And then just tell me the recrystallization in a nutshell.
You can take half of the crystals after you filter it.
Yes.
And dissolve them in water.
Yeah, and how much water?
That's a good question.
You need to dissolve it in a minimum of water. To dissolve it in a minimum of water, get your stir rod and crush up the crystals. If you still see crystals left, add a little bit of water, but you don't add too much water. Otherwise, you're never going to get crystals again. And then once you dissolve it in the minimum of water on heat, then you can add the ethanol. We don't have distilled water. We have deionized water. It's a little bit different, but with the deionized water. Distilled water is too expensive for us.
Is that really close to 7?
No. The deionized water, distilled water is close to 7 if it hasn't been exposed to air. And in fact, I need to talk about that. So we're going to use the deionized water. I used to use distilled water all the time. It's great, but expensive.